here to the right, we're going to have a small vertical displacement in the y direction from there to there. That's some dy, and there's our dx. We can find that by taking the differential. Dy is equal to the derivative of this, which is minus L times the sine of theta times d theta, and we can find the small change in x, the virtual change in x, what we call the virtual displacement. Dx is equal to, that would be 2L times the cosine of theta times d theta. So now we're going to describe the virtual work done. So I'm going to say that the virtual work done is equal to the sum of all the forces from I equals 1 to n times all the displacements. Now notice that the reactionary force of A sub x and A sub y do not aid in the virtual work done because there's no virtual displacement here. That stays in place. We're only going to allow this portion to move in a virtual sense. So the only three forces that contribute is F, because there's a vertical displacement there, B sub x, because there's a vertical displacement here, and B sub y, however, think about it, if the displacement is in the horizontal direction, and the force is acting in the vertical direction, the angle between those is 90 degrees, and the cosine of 90 is 0, which means we only need to take into account this force and B sub x. Those are the only two contributing forces to virtual work done. So now we can say that this is equal to, oh, and by the way, of course, this must be equal to 0 because the system is in equilibrium. So now we can say that the first force, F, we have to be careful here because we do have to take into account that these are vectors, and we're doing the dot product. These are vectors, and we're doing the dot product here. Now, when you do a dot product, you take the magnitude of F, that's the magnitude of dy, times the cosine of the angle between them. So in this case, we get F times dy, and dy is defined here, but we need to take the magnitude of dy, so this becomes L times the sine of theta d theta, times the cosine of the angle between the two, but since they're both acting downward, the angle between the two is 0, so we take the cosine of 0 degrees, plus b sub x times dx, now dx will be 2L cosine of theta d theta, 2L cosine of theta d theta, times the cosine of the angle between them. Now notice that dx is pointing to the right, and dx is pointing to the right, so they're both pointing in the same direction, the cosine of 0 degrees. And of course that's equal 0, and equal 0. Alright, now notice this is equal to 0, both terms have an L in them, so L cancels out. Both terms have the d theta in it, so that cancels out. So we're left with, on the left side, we have F times the sine of theta times 1 plus b sub x times 2 times the cosine of theta times the cosine of 0, which is 1, and that equals 0. So now we can move F sine of theta to the right side. So times minus F times the sine of theta. And now when I divide both sides by 2 times the cosine of theta, I get b sub x is equal to minus F over 2 times the sine divided by the cosine, which is the tangent of theta. And this is the force b sub x. Now, it's negative. The reason why it's negative is because b sub x is actually acting in the opposite direction. If I push down on F, then this member will try to slide to the left, the block will hold it in place by pushing, it will try to slide to the right, and the force b sub x will act to the left and keep it from going to the right, so therefore b sub x is a negative F over 2 times the tangent of theta, indicating that the way I've drawn it here is in the opposite direction from the way it actually acts. So that's how we find any forces on any members by using virtual work. Even if we have a completely constrained system, we can still imagine that some part of it could move, make it move in a virtual sense, and then we calculate the virtual work done on that small amount of displacement. And that's how it's done. Welcome to lecture online. Work done by either compressing or elongating springs is a very typical type of problem. And here we have such an example. Let's say that this is the natural position of the spring, so no force is applied. Then to extend the spring from there to there, you will need to apply some force. And as you continue to extend the spring even further, it will require a greater and greater amount of force. So you might be able to indicate that this takes a small amount of force, and as you elongate the spring further, it will require a greater and greater amount of force. So the force is not a constant. What we're trying to do here is determine how much work will be required to extend the spring from a distance of 1 meter past its equilibrium point to a distance of 3 meters past its equilibrium point. Notice that the force required is indeed a function of x. It is equal to 1/2 kx squared, where k is considered the spring constant of the spring. That can be determined by taking the amount of force required to extend it or elongate a certain amount of distance. In this case, it required a force of 100 newtons to elongate the spring by 1 meter, so therefore the spring constant for this spring is 100 newtons per meter. So now, to calculate the work done, to extend it from 1 meter to 3 meters, we can do it as follows. work done is equal to the integral from x equals 1 to x equals 3 over the force times dx. So what we're going to do here is we're going to pull the string just a small amount of dx from this position to the next position, calculate the work done, extend it again, again, and again, and we'll sum them all up going from 1 to 3. That's, of course, the integral. And so this can now be written as the integral from 1 to 3. The force is 1/2 kx squared dx, and of course, since the 1/2 is a constant, we can move that outside integral sign, so this is equal to 1/2 k times the integral from 1 to 3 of x squared dx. So now we're able to integrate that. We'll integrate x squared, we get 1/2 k times x cubed over 3, that's evaluated from 1 to 3. So we can take the 3 out, so we can bring it over here. We have this is equal to 1 over 6 times k. When we plug in the upper limit, we have 3 cubed, which is 27, minus when we plug in the lower limit, we get 1. And that would be equal to 26 over 6 times k. This is equal to, when we simplify that, we get 13 over 3 times k. And since k is equal to 100 newtons per meter, that's equal to 13 times 100 divided by 3. And of course, 1300 divided by 3. Oops. Well, let's see here. Actually, something to calculate for that. 400 divided by 3 is 400. That would be 433 and a third. And with that would be in terms of the joules. And that's how it's done. Welcome to our lecture online. Now let's take a look at welcome to our lecture online. Now let's take a look at eclipsing binaries to see how we can determine the size and mass of these stars involved in the eclipsing. Well, first of all, we can identify the light coming from the various stars, the intensity of the light, when we look at certain bands of light. We have the 1.6 micrometer band, which would be strong for red stars, and relatively weak for blue stars. And I say relatively weak relative to the total intensity. We're going to look at the V band and the B band. The V band has the longer wavelength, so it would be stronger, relatively speaking, again, for the red, orange, or yellow stars. The B band is relatively stronger. The intensity of that band, we can then expect it to be a much hotter star, like a white or a blue star. Coupled with using the second Boltzmann law, where the amount of light per unit time or energy per unit time received from the star is equal to the emissivity constant, the Boltzmann constant, the area surface area of the star is essentially the fourth power, and coupled with Wien's law that relates the highest intensity of wavelength that we receive from the star to the temperature, we can then use that and the color-luminosity relationship of the HR diagram to try and determine the kind of star that we're dealing with. Obviously, when we have the color of the star determined by using certain filters, we can then pretty well approximate using the HR diagram what type of star and what size star we're looking at. Another way which we can determine the size of the star is to realize how much the light is being dimmed. Now notice when the small star is behind the large star, we have a dimming of that light, and so we can then determine how much light reduction is there because the small star is no longer being seen. Here, this is the reduction when the small star is in front of the large star, and lots more light is being held back. But then if we add the reduction of the small star to this, we can then see this would be the total reduction if no light were received from the small star that's in front of the large star. And so based upon that, we can also determine what size star we're dealing with. Another thing that we can do is figure out, once we know the orbital radius, and we know the period is of course easy to calculate, but if we can somehow measure the orbital radius, then we can determine how fast the star moves, the small star moves around the large star, we can find the tangential velocity of its orbit, and then we can determine the diameter of the small star by measuring how long it takes for the star to disappear completely behind the large star, or for the star to disappear in sense completely from the large star, either way. So we can see how long that takes, and so we multiply that time times the velocity to get the diameter of the small star, or the amount of time that it spends behind or in front of the large star, we can then determine the diameter of the large star by multiplying the tangential velocity of the small one times the time that it spends hidden by the large star. So those are some of the techniques that we use to try and determine the mass and the size of the stars in eclipsing binaries. Of course, you want to see some examples of how we exactly do that to get more of a feel for it. But at least at this point, you have some good ideas of the different types of techniques we use to come up with the size, the mass, and the size of the various stars in eclipsing binaries. And that's how it's done. Welcome to our lecture online. Here we have a system that is partially constrained. On the left side of the system, it's attached to a block. It can swivel this way, but it cannot move either up or down, left or right. This member here is attached to this member. This member can actually move to the right and push this block to the right, so therefore there is a force pushing to the left. I have a force trying to drive the members down. I have a force here to the left. We have two reactionary forces. We have one at A and one at B. Of course, at A we have both one in the X direction and the Y direction. The one at B we only have one in the Y direction only. So this is the D sub Y, if you want to call that. Okay, but since b sub y is pointing perpendicular to the change in the direction, the x here, that means the angle between the two is 90 degrees, so that way we can simply ignore b sub y, and we can ignore a sub y and a sub x because this point right here does not move at all. So there's no virtual work done. So what we're going to do first is we're going to define the initial distance from here to where the force is acting initially. We're then going to define the change in the distance dy. We're also going to define the distance x from here to here, and then the distance dx. So based upon the angle relative to the vertical, and we assume that this is going to be the same on both sides, we can say that y here is equal to the length of this member times the cosine of this angle because it's adjacent to the angle. So we can define y sub naught as being equal to the length of the member times the cosine of the angle theta. We can also define x here, well, that would be L times the, well, if we put the x over here, that would be opposite the angle, so this would be L times the sine of theta, but we have to multiply times 2 because there's two members there. So that means that x sub naught is equal to twice the length of each member times the sine of the angle theta. Now we can find the change in y and the change in x in terms of the change in the angle theta. We're just going to circle down to a small angle d theta, which means that dy d theta can be found by taking the derivative of this. That would be, well, the derivative of cosine is the negative sign, so minus L times the sine of theta, and then we bring this d theta over here. We can simply write that dy is equal to minus L sine theta. Same with change in x. Dx can be defined as being the derivative of this, which would be 2L times the cosine of theta d theta. So now we have defined the change in y and the change in x in terms of the change in the angle. We're now going to try to find r in terms of how much the angle changes and the force F applied at the top. So for that we're going to use virtual work. We can say that the virtual work done is equal to the sum of all these forces, I equals 1 to n. In this case, there's only two forces at play. B doesn't do any virtual work, neither does A sub x and A sub y. Only R and F do virtual work. So it's going to be the product of the forces multiplied times the du's. Of course, it's a dot product, so we do have to take into account the directions of those. And we know that that is going to be equal to 0 because the structure here is in equilibrium, and now we're allowing it to do a small amount of virtual work. Of course, virtual work means we have an imaginary displacement. There's really no real displacement, and we're going to calculate the work done by doing so. So this is going to be equal to the force F, the magnitude of the force, times the magnitude of the displacement dy, times the cosine of the angle between the two. But since they're both pointing in the same direction, that will be the cosine of 0 degrees. Plus the force here, r, that's the magnitude of the force, times the magnitude of the displacement dx, times the cosine of the angle between the two. Now r is acting to the left, dx is to the right, which means the angle is 180 degrees. And that should add up to 0. Alright, now let's go ahead and simplify this. So this is equal to f times dy times the cosine of 0, which is 1, and then minus, because the cosine of 180 degrees is minus 1, so we're going to get rid of this equal sign here. So f dy minus r dx times the negative 1, which I placed there, equals 0. Now keep in mind that f and r are the magnitudes of f and r, and dy and dx are the magnitudes of dx and dy, because we're taking care of the direction of the virtual displacement by taking the cosine of the angle between them. Alright, now let's plug in what dy and dx are equal to. So here we have f times dy, and we need to know the magnitude of dy, which is L sine of theta d theta, minus r times dx, the magnitude of dx, which is times 2L, the cosine of theta d theta, and that should equal 0. Now notice, since it's equal to 0, we can factor out an L, we can factor out the d theta, so we divide both sides by L, we can divide both sides by d theta, and now we're left with f times the sine of theta is equal to, minus 2r times the cosine of theta is equal to 0. So now I can move the 2r cosine of theta to one side, and this on the other side, so we have 2r cosine of theta is equal to f times the sine of theta, and now we divide both sides by 2, and both sides by the cosine of theta, we can write that r is equal to half of f times the tangent of theta, because the sine divided by the cosine, of course, is the tangent. And so now we have found the magnitude of r in terms of f and the angle theta. So at the moment that we're in this particular position, and of course f is applied, r will be equal to half of f times the tangent of theta. And that's how it's done with virtual work. I'm hoping you're beginning to like this method, because it turns out, as the structures become more complicated, it actually becomes a very easy, straightforward way of solving for the forces on the members of a structure like that. And that's how it's done. Welcome to our lecture online. Here's the first example of how to calculate the work done by a force. Let's assume that the force is defined as a function in x, and there it is, 2x squared plus 3x, and the units of force are newtons. let's say we move an object, or we do force over distance from x equals 1 to x equals 3, and again, the units for distance would be meters. And if you combine those two units, the units of work are done newtons times meters, which are joules. So that's named after the French mathematician, physicist, scientist called Joule. Now, we define the work done as being the integral of f dot dx, so we move the force over very small distance dx, we sum them all up from a to b. In our particular case, that is equal to the integral from x equals 1 to x equals 3 of the force, which is 2x squared plus 3x times dx. So we integrate that, and we get the following. 2x cubed over 3 plus 3x squared over 2, evaluated from 1 to 3. So we plug in the upper limit, and then we subtract and plug in the lower limit. So this becomes 2 times 3 cubed over 3 plus 3 times 3 squared over 2. And now we subtract from that. When we plug in the lower limits, it will be 1. So when we plug in 1 here, we get 1 cubed, simply 2/3. We plug in 1 here, which is 1 squared, simply 3/2. So we have subtract 2/3 and 3/2. Alright, so simplify that a little bit. The 3 will cancel out 1 these 3's, so that will give us 3 squared, which is 18. Yes, that is correct, so that's the son of it. So 3 cubed will be 27 divided by 3, which is 9. 9 times 2 is 18. Plus, here we get 3 squared, which is 9 times 3, which is 27, divided by 2. And then from that, we subtract 2/3, and we subtract 3/2. Okay, simplifying this, notice we have 27 divided by 2 minus 3, that's 24 divided by 2, so this is 18 plus 24 divided by 2 minus 2/3. And of course, 24 divided by 2, that's 12, so that gives us 18 plus 12 minus 2/3, which is equal to 30 minus 2/3, which is equal to 29 1/3. Of course, the units for that would be newton meters or joules. So the amount of work done by that force, moving from x equals 1 to x equals 3, the function of the force defined by this gives us work done of 29 1/3 joules. And that's how we start. Yeah, the mathematician sometimes come in handy. So welcome to our lecture online. Here we have a quick overview of eclipsing binary star systems. First of all, they tend to be very close together. Here we have the diameter of the large of the two stars. Here we have the small star. And notice that the distance from the small star to the large star approaches the diameter of the large star. So you see that the ratio of the distance to the diameter of the large star approaches 1. And that is typically what we need in order to see eclipsing binaries. When the stars are too far apart, the chance of one eclipsing the other is very minute, because any angle away from the perpendicular, you can see that the star would end up being below or above it. So typically, star systems, binary star systems that are eclipsing, tend to be very close together. Now, this is the line of sight from Earth to a binary star system. You can see then that the orientation of the orbit, if we draw that as a flat plane, and we have the angle normal to that, so this is called the unit normal, which is perpendicular to the plane of the one star revolving around the other star. The angle with the line of sight is called the angle of inclination. And for most binary star systems that are eclipsing binaries, that angle becomes pretty close to 90 degrees. If it's close to 90 degrees, then we typically have a situation where we have a total eclipse. The small star will move completely in front of the large star, and will move completely behind the large star. But if the angle is a little bit farther away from 90 degrees, we can have a case where the star grazes the other, not physically touch, of course, but in the line of sight. And so we have what we call a partially eclipsing binary, where we have just part of the large star being hidden by the small star, and the small star partially being hidden by the large star. We can usually tell by looking at the light that we get from the star system. Notice when one completely disappears behind the other, and there's a fairly large difference in the size, we can see that it spent some time behind, and spent some, or I should say in front, and spent some time behind the large star. If we have a grazing situation where we have a partially eclipsing binary, you can see that the light diminishes and then starts going back to its full strength, and we don't have that period where one will stay behind the other or in front of the other. Typically, in a eclipsing binary star system, we will know the period. It becomes quite obvious because of the light that we receive from it, and we can usually calculate fairly closely the angle of inclination, again, based upon the kind of light curve that we get from observing the binary or the eclipsing binaries. So this is at least a general overview of what they are, and we'll look at them in a little bit more detail in the videos to come. That's how we start. Now let's take a look at the principles of virtual work. There are 3 of them. The first 2 are already familiar with. Principle 1 states that if a particle is in equilibrium under the action of a number of forces, this includes the inertial force NA, so even if the forces do not add up to zero, if the net force is not equal to zero, but we include the inertial force NA, then they will add up to zero, then the